Excellent. Well, thank you so much for the invitation to speak at this conference and also for organizing it. It's been a real pleasure to be here. All right, so today I will be talking about string amplitudes, and most of what I will say is based on the work in collaboration with Lawrence Eberhard. All right, so as I mentioned, the topic of this talk will be scattering amplitudes in superstring theory. And while there could be many motivations why you would look at those objects, for the purposes of this talk, I will just look through the lens of a single problem, which is that of high-energy scattering in string theory. All right? So as a word of motivation, I just decided to pull up some motivational paragraphs from this famous paper of Gross and Mende, who say that it is widely believed that when string theory is explored beyond the string scale, a fundamentally new physics will emerge, and perhaps spacetime itself will lose its meaning and will have to be replaced with something else. All right, what I love about this problem is that we actually seem to have a very good handle on what exactly we need to compute. We need to look at the high energy limit of scattering amplitudes. All right, so there's multiple setups that we can consider, but for the purposes of this talk, I will be looking specifically here at 4-gluon scattering. More specifically, it's planar contribution, so single trace, in type 1 superstring in flat space in 10 dimensions. All right, so the setup is very clear. We smash together two strings, two other strings come out, and the kinematics is described, first of all, by the scattering angle here that we will keep fixed. So for example, in a lot of plots that I will be showing in this talk, we'll fix it to 60 degrees, just for concreteness. And there's also other variables in this problem. So we have the center of mass energy squared that we typically call S, which is taken to be much, much larger than 1 in the units of alpha prime. And of course, S has to be positive. All right? So we take S to be very large, such that the ratio of S and T, which is related to the scattering angle, which we keep fixed, so that ratio has to be fixed as well. And if you're talking about real energies and real angles, then that ratio has to be negative. So S has to be positive and T has to be negative, while both of them become very large. Right. So this question turns out to be way too difficult to understand in full generality, at least when it comes to fine details. So what we'll do is we'll use perturbation theory. So on the left here, we have the planar contribution to the amplitude, which is a function of S and T. And we're going to expand it in terms of the genus expansion. So at the leading order, we have the disk contribution, which is very well understood for all intents and purposes, as I will reveal in a second. And then in the first subleading correction, we have these two one-loop contributions, so genus 1 contributions, one coming from the annulus topology and the other one coming from the Mobius strip. As I will try to argue, while we can do a lot of computations about those types of amplitudes, in full generality, those amplitudes have not been yet computed at finite energy. All right, so this will be the subject of my talk. Before I go further, I have to also mention that superstring perturbation theory, of course, comes with a lot of caveats. So since I only have half an hour in here, I will not have time to discuss all of those caveats, but I actually would recommend that if you're interested in those problems that typically contribute at higher genus order in perturbation theory, I would refer you to these very nice talks early on in the same program by Oliver Schlotterer and by Ashok Sen. All right, so since I mentioned I wanted to compute the amplitudes, well, we'll have to agree what exactly does it mean to compute an amplitude, all right? So for the purpose of this talk, I will be very, very pragmatic. I will call it the particle physicist approach. And the approach is as follows. By whatever means necessary, I don't really care how you get it, just give me numbers, all right? So if I take my scattering amplitude and I plug in some values of S and T, I just want the final numbers that it evaluates to, hopefully to an arbitrary number of digits and so on. And once I have that, I can basically probe whatever physics I want. I can study it in high energy limit, low energy limits, study its analytic structure, and so on. All right? So it turns out that if that is your criterion for what you consider a computation, then it turns out that it's actually nearly impossible to pull this off, even in perturbation theory, and even at the lowest orders in perturbation theory. So this is something that I wanted to discuss next. We're going to study with the simplest contribution. The leading order is given by the famous Veneziano amplitude. This is how it looks like. So it's the planar contribution at tree level is a function of Mandelstam invariance S and T, as I discussed before. All the polarization dependence, so the dot products of the external polarizations and the momenta come out in this single factor that we will call the T8 tensor, all right? So since this is an overall factor, when it comes to plotting the amplitudes, discussing it, I would just ignore it, so set it to 1. And all the beauty of string theory is hidden in this collection of gamma functions in here that depend on the S and T, but also on the inverse string tension, which to make the formula shorter, I will set to 1 often as well. All right? So this is, of course, a beautiful formula. You can read off a lot of physics out of it, the positions of the resonances, you will discover super Young-Mills in the leading alpha prime expansion. You can look at the high energy limit and so on and so on. But for the purpose of this talk, what we'll try to do is we'll try to get numbers out of it. So here's the kind of a plot that you would get if you compute the Veneziano amplitude at the fixed angle, which corresponds to taking the ratio of S and T to be fixed, for example, 60 degrees in here. And for the plotting, I will also multiply it by the sine pi s and sine pi s plus t, which basically remove all the zeros and poles of the amplitude so that it's easier to look at, okay? Now it's a smooth function, all right? Notice that here I'm plotting it on the log scale, and the function goes to roughly a linear. So what this tells you is that at high energy, it is actually exponentially suppressed. This is the famous exponential suppression that tells you that the amplitude goes like e to the minus alpha prime times the tree level on-shell action. Okay, in this case, it's going to be some number, and we're just going to get an exponential suppression. All right, so that was very easy. So now let's go one loop level higher. Let's go to one loop in which we have two topologies, the planar annulus and the Mobius strip. Right? So by now, what I'm going to show you, this is a textbook result. You can find it in any book on string theory. And it's a result of doing the OPE computation on the worldsheet. All right? So let me just dissect it a little bit. So here we have a collection of Jacobi theta functions as a function of the differences between positions of the vertex operators, as well as the modular parameter tau. And the S and T dependence is here in these exponents, all right? So the setup is, of course, that we map everything into a rectangle. We identify the two sides of the rectangle, this one and this one. We insert vertex operators on one of the boundaries, and we can fix one of them by the rotational symmetry of the problem, okay? For example, Z4 to 1. And the additional variable that we have is the tau, which is the modular parameter. In this case, it's purely imaginary and positive. Okay, so when we do the integration, we have to integrate over the positions of the punctures, okay? Here in this specific order, which basically corresponds to the planar ordering of the vertex operators. And we also have to integrate over the modular parameter from 0, which corresponds to very thin annuli, to all the way to I infinity, which corresponds to very thick ones, all right? And just like as we've seen at tree level, the polarization dependence just goes up front. So once again, we really don't have to worry about it. Okay, so this was the contribution from the planar annulus. Now we can discuss the contribution from the Mobius strip. It turns out that as a result of doing the computation, doing all the spin sums and OPEs on the worldsheet, the result can be actually summarized by computing the same integrand, except evaluating it on a different contour in the tau plane. So here we have a shifted contour, where instead of 0 to I infinity, you go from 1/2 to 1/2 plus I infinity. All right? There's actually another difference that the minus sign that we used to have in the annulus contribution now becomes a plus with 32 over n, where n is the one from the SON. Okay? So of course the annulus contribution, if n was large, would be 1 over n suppressed, except in string theory, we'll see that n is of course fixed to 32. So it's no accident that this ratio appears. Okay, awesome. So that's great. So we have a formula. So how about we just plug it in and then we can make a computation, all right? So what I'm going to do is I'm just going to write this mathematical code here. This is literally just transcribing what was on the previous slide into a mathematical notation, and I'm going to plug in some numbers. S is positive, T is negative, blah, blah, blah. And I'm going to click Shift-Enter. Okay, this is an example that I've actually done as a graduate student. And maybe some of you would know already what the result of that computation is. The result is this. So Mathematica complains that not only there was a loss of precision, the loss of precision was in fact catastrophic. Right. So that is not an accident. It's not an issue with the software. It's actually a fundamental issue about string perturbation theory. Okay, so the bottom line here is that the formulas for string amplitudes, typically, they cannot be used in practice. So this is very much symptomatic of the generic case. Okay, so let's try to understand why. So first of all, I wanted to emphasize that what we're looking at here is really a physics problem. It's not a computer science problem, it's not a math problem, it's really about physics. Okay? So let's try to diagnose why it happens. So first of all, the first problem is that if you inspect the integrand that we've seen on the previous slides, it was actually purely real. All right? And the measure, after you correct it with the factor of I from the fact that we are on the imaginary axis, is also real. So not only the answer is infinite, it's infinite and real. Okay, so we know straight away that this looks fishy, and the reason why it looks fishy is that this could not be possibly compatible with space-time unitarity, which tells you that S as dagger is equal to 1. So the scattering amplitudes has to have a phase. It cannot be purely real, because otherwise it would have to be trivial. All right, so there's the first problem. And let me just give you an analogy of how this would look like in QFT. In QFT, the problem would be roughly of this type, that if you wanted to do some loop integration of some loop integration variable, and you had your propagators, but you forgot the I epsilons. So of course, you're trying to integrate, but you hit this pole on the integration domain, so you get infinity. Okay, so all the problem is because we forgot about including the I epsilon in string theory. And just like in QFT, we know very well that we're supposed to add the causal I epsilon prescription, which shifts this mass squared with a minus I epsilon. The question is how to do this consistently on the worldsheet as well. All right, so in fact, I'm going to distinguish between two separate challenges in this general area. The first one is the conceptual question of what is the integration contour on the moduli space of Riemann surfaces. And equivalently, you can think of it as a question about physical compactification of the moduli space. Okay, so let me emphasize something that I'm sure is very well known to the experts, but probably not widely known, is that the math constructions, such as the Deligne-Mumford compactification, in this case don't work. So they don't resolve the problems that we've seen on the previous slide. And what is going to resolve the problem is to think about this I epsilon in string theory, which in fact has been discussed over many years by multiple authors, most recently by Edward Witten around 10 years ago. His work was in fact the main inspiration for ours. All right, after you resolve this conceptual problem, what you're left with is a computational problem. The computational problem is going to be how to actually integrate over this contour. So we're going to see that. And essentially, we're going to see that the integrand will have a lot of large oscillations that cancel out in the end. So we'll see a form of a sign problem. And the question would be how to resolve that issue as well. And here we actually use the so-called Rademacher construction that has been employed to deal with similar problems in number theory computations. And maybe you could have seen some of those constructions used in previous work on CFT, in which the Rademacher expansion was already employed before. All right. So before starting doing the actual computation, let me kind of review what is currently known, what has been known before about the one-loop contribution, how it could possibly look like, and we're going to try to guess if we could have arrived at it by other considerations. Okay, so what are some basic constraints that the one-loop amplitude has to satisfy? The basic constraint is that it has to be compatible with unitarity. So what this means is that if you draw a unitarity cut, then there's going to be some on-show states running, the string states running through the loop. And this tells you that immediately that string amplitudes will have an infinite number of discontinuities, and the discontinuities will appear exactly when you cross the threshold for the particle production of the intermediate masses. All right? And because the masses are quantized, or masses squared are quantized in the units of 1 over alpha prime, then this tells you that the amplitude will have to be a crazy object that, as a function of s, will have to jump every time that s crosses this value of the square root of an integer plus square root of another integer all squared. In fact, I think this is essentially the reason why the analytic form for these amplitudes isn't known. If there existed one, it would have to be some crazy function that somehow has this property, and it's not entirely clear how to write it down. But if you have some ideas, please let me know. Okay, so the tentative plot will look something like this. Okay, so let's say we're going to plot the one-loop contribution at fixed angles. So s is this, and t is equal to minus s over 4 as a function of s. And the only thing that we know about it, hopefully you can see these dashed lines in here. These are just positions of all possible thresholds that can appear. Okay? So for example, this is s is equal to square root of 3 plus square root of 5 all squared. Another idea that you might have had is that, well, there's been a lot of developments in trying to understand the alpha prime expansion of string theory. However, the alpha prime expansion is, of course, going to break down at the position of the first resonance, so we actually can't use it in practice if we wanted to make a plot of an amplitude at higher and higher energy. Okay, so next question is, what about the asymptotics? Do we know something about strict limit as alpha prime goes to infinity? And in this case, there's something, we can employ the saddle point approximation at fixed angles. So this is the approximation in which the alpha prime goes to infinity in such a way that s over t is fixed. So in principle, this could be, for all we know, there is going to be a large number of saddles, possibly infinite, that are going to dominate this asymptotics with some value of the on-shell action and some coefficients up front. Okay, however, we have a working hypothesis that dates back to the work of Gauss, Mende, and Magnus in the open string case, which tells us that there is going to be one particularly symmetric saddle, which corresponds to the value of the action equal to that at tree level. And the statement is that this saddle is in fact dominant. Okay, so we're going to use it as a working hypothesis, but let me actually emphasize that, of course, we don't know if that statement is true, because at this stage we don't even know what the integration contour should be. And the way that we run the integration contour is going to decide of which saddles are you're supposed to be picking up. Okay, but nevertheless, we can just put some tentative high energy behavior on our plot. So our plot will have to look something like that on the log scale. Once again, it will have to asymptote to some straight lines like this. All right, excellent. So in fact, we know even slightly more. The additional piece of information that we have is that we can look at these specific degenerations of the worldsheet in which we pinch the cycles in here and in here for the annuals and similarly for the Mobius strip. So the way that this looks like is that it looks like the bubble contribution of a Feynman diagram. This, in fact, immediately tells you that there's going to be double poles of the amplitude. The reason for that is that in this bubble, there's a propagator in here, and there's a matching propagator on the other side. Okay, so each of them give you a simple pole, and the overall contribution will have to have a double pole. So let me just call the coefficient of this double pole sigma. And now we wanted to interpret sigma as a part of the 1pi, the Dyson resummation, just like in quantum field theory. So in fact, sigma carries a lot of physics information. The physics information that it carries is the, roughly speaking, the real part of sigma is going to be related to the mass shifts in some average sense, if we bunch up all the states at a given mass level n. And likewise, the imaginary part is going to tell us about the average decay waves. Okay? And we're lucky here because these quantities have been actually studied quite a lot in the previous literature. So what we can do is we can take these results and then we can see what kind of constraints they give us on our scattering amplitude. And just as before, I'm going to multiply both the real and the imaginary part in orange and blue respectively by a sine of pi s all squared. So what this is going to do is it's going to just remove the double poles at integers, and it's just going to make them the plot into a smooth plot. Okay? It turns out if you get the data from the literature and you try to plot it, for the imaginary and real part, they align themselves along these two lines. Okay, so we get a data point at every integer. And let me actually emphasize something here. This is not a mistake. So the blue is the imaginary part. It is actually leading, on average, by 2 or 3 orders of magnitude over the real part. So the imaginary part is leading. What you might have thought before, that these I epsilons are kind of some subtlety, they're just going to fix something up, but they don't really matter, is completely false. What it tells you is that if you ignore the imaginary part, you will be making a mistake of order 10 to the 2 or 10 to the 3. Okay, so now let's go back to the contour. Basically, we've exhausted all the mileage from the literature. And now we can actually try to address the problems that we've settled to solve. Okay, so let's look at the contribution to the annulus topology in the tau plane. So this is the modular parameter, and we integrate from 0 to I infinity. It turns out that there's no problems anywhere along the integration domain where the integrand is in fact holomorphic. The problems arise from the two endpoints, at 0 and at I infinity. So 0 corresponds to the configurations in which the worldsheet becomes a very thin annulus. Okay, so roughly speaking, it looks like a Feynman diagram. And this is going to be exactly the place where you need to be careful about the I epsilon. One way that you diagnose this problem is that if you look at the integrand, it involved a lot of elliptic functions. Those elliptic functions, in fact, have a bunch of infinite number of essential singularities on the real axis for every rational integer. For every rational number. In particular at 0, and what happens here is that we approach the essential singularity from the wrong side. Okay, likewise, there's going to be a problem that when tau goes to I infinity, so this is the limit in which the annulus becomes very thick, and roughly speaking, you can think of the internal boundary here as shrinking to a point, but there's no momentum flowing to that boundary, so it's as if we inserted a soft particle at 0 momentum, okay? So this actually causes a divergence, and it turns out that divergence is just there. You cannot cure it just at the level of the annulus alone. Okay, but let's not worry about that now. Let's worry about the I epsilon first. Okay, so the idea is going to be to replace the contour that I've drawn on the previous slide with a new contour that implements this Witten I epsilon prescription. Okay, so let me just emphasize straight away that what I'm drawing here is not a contour deformation of the previous contour. Instead, it's a new prescription. Okay, so the prescription is going to be, we're going to integrate all the way to 0, except we're going to stop at some small value, and then we're going to go on a semicircle and approach the essential singularity from the right-hand side, instead from the top. Okay, so it turns out that this is actually, as described by Witten, is necessary for consistency with QFT causality, or more specifically, with the QFT I epsilon prescription. Okay, so as I said, the only difference to previous slide is that we approach the essential singularity from the right, as opposed to from the top. All right, so it turns out you can actually analyze the Mobius strip at the same level. You just turn in, and you go on a hook, and then you approach 1/2 from the same direction. Okay, so that solves the problems close to the real axis. Now we are still left with the problems at I infinity. However, recall that there was a difference between these two contours. There was a numerical factor of a minus, which I've absorbed into switching the orientation of the contour. And also there was a numerical factor of 32 over n. Okay, so both of these contributions individually diverge, but they cancel out if that factor is 1 or n is equal to 32. This is the famous soft-dilaton cancellation mechanism in planar type 1. Okay, so next what I wanted to do is I wanted to plot the imaginary part of this amplitude. So these hooks sticking out to the right correspond to adding the plus I epsilon. You could have repeated everything in the same way with a minus I epsilon instead, with hooks sticking to the left. And now we can compute the difference between the two. So the difference is that everything is going to cancel except for these little semicircles that now are completed into full circles. Okay? But recall that there was nothing specifically that told us that the size of the circle is supposed to be this one. In fact, the function is entirely holomorphic in the upper half plane minus the real axis. So what this tells you is that you can actually shrink them to be arbitrarily small, but not zero. And this turns out to be the secret sauce behind this computation, that essentially you think about shrinking these circles to be very, very small, and now you probe your integrand only in the neighborhood of these 2 points, tau equals 0 and 1/2. So you can just Taylor expand it, and that simplifies a lot the main computation. Okay? So while the computation is actually technical, what I can show you is just the final result. The final result is that all of a sudden we get a plot of the imaginary part of the amplitude. And it looks like this. The cool part about it is that we've actually checked. This satisfies a lot of checks, including check of unitarity cuts. It also matches the integer points that we've had before. So it seems like a solid result. All right. So you might notice these spikes that stretch out here. But recall that we plot things on a log scale. The spikes just mean that these are the zeros of the imaginary part. Okay, so as you can see, on average, this imaginary part actually follows the exponential decay up to some wiggles. So it's actually not clear at this stage if these wiggles are going to settle down to a smooth function, or maybe there's some competition between different saddles that have the same real part but a different imaginary part, or some mechanism like that. This is still an open question. All right, and another thing that I wanted to comment on is that this blue curve, in fact, has a number of discontinuities exactly where they need to be, but they're actually barely visible. So if you zoomed in, you would have seen them. But the reason why they're barely visible is that we actually have analytic control over that. We understand how slowly they open up. Okay? All right, so now the question is, to complete our story, we wanted to also ask not just about the imaginary part, but also about the real one. Okay, so let's come back to the contour from the previous slides. And let me notice, first of all, is that it was holomorphic in the upper half plane, or the integrand is holomorphic in the upper half plane. So we can simply deform the contour, and we're going to separate it by the part that goes to infinity and the part that goes down. Okay, so the part that goes to infinity was previously computed. In fact, it gives rise to this effect of the alpha prime renormalization. Roughly speaking, you can think of it as the fact that a disk with a soft dilaton is going to be equal to the alpha prime derivative of the Veneziano amplitude. So this part can be actually computed exactly. But now the difficult part is in analyzing the rest of the contour. All right. So in order to analyze the rest of the contour, let me go into a small detour into some number theory. Okay? So let me first introduce the Fari sequence with FQ, which is going to be set of all irreducible fractions between 0 and 1, such that the denominator is bounded by Q. Okay, so for example, F1 is going to have these two fractions. F2, we add up a half. At F3, we add a third and 2/3, and so on and so on. So why is this interesting? It's interesting because now we can introduce another construction, which are called fourth circles. And these are going to be circles that touch the real axis at exactly some fraction and with some specific radius in the tau plane. All right, so you draw these fractions, and then you draw the circles with this exact radius, and you get the following picture. And the fact that they touch is not an accident. It's actually the reason why we've chosen the specific radii. And now the question is, how is this useful for our purposes? Okay, so let me mention, of course, that each circle can be mapped to the big one, which is the one that we've already computed by a modular transformation. Okay, so this leads us to this notion of the Rademacher contour, which is newly 8 years old or so. And the prescription is as follows. For a given Q, we're going to follow all the fourth circles in the sequence FQ from 0 to a half. Okay, so let me first describe gamma 2, which is the simplest case of the Rademacher contour, in which we follow the circle at 0, and then we stop when it touches a half. Then we turn around, and then we follow it all the way to a half. Okay, so that contour is, of course, the contour that we're interested in. Is the one that was approaching 0 and 1/2 from the right-hand side, and otherwise it just goes somewhere in the complex plane. Okay, so the idea is to just keep doing that over and over. So you keep adding more integers, or more fractions, rather. And then you do this turning game that you flow around until you meet the next one, and so on and so on. And then you can keep going with this procedure, and you can extrapolate all the way to infinity, which essentially is going to close the fact that these are not complete circles yet. It's just going to flow around all of them. So in the limit, we enclose all the circles exactly once. Okay, so we get a contour looking like this. This looks a bit insane. But it turns out that this is the reason why our computation can be in fact done. And the reason for that is that now, instead of a contour that was running into the complex plane, along the imaginary axis, now what we can do is we can in fact shrink all of the circles, and essentially we have a sum over rational points. Okay, so roughly speaking, this will give us a representation of the one-loop amplitude that sums over all the rational points. You have to perform the circle integrations, and all of them are 1/q suppressed. All right? So if these integrations, so each individual integration is something that we already know how to do because it was a contribution to the imaginary part, right? So if these terms in the sum have enough phases so that phases cancel out, then this is a convergent series. Okay, so long story short, after that statement and 100 pages of additional algebra, you arrive at the final plot of the planar scattering amplitude at one loop that also contains the real part in here. Okay, so the real part looks as follows here in orange. Once again, we see a lot of spikes. These spikes are just the zeros of the real part, and we see a lot of oscillations. Much more than for the imaginary part, okay? And another qualitative feature that we see is that, once again, they, roughly speaking, follow the envelope settled by the exponential decay of Gauss and Manius. Okay, so just to wrap it up, let me just mention that this is, of course, just the tip of the iceberg. We have all this technology, and I try to kind of view it through the lens of trying to analyze the high-energy limits. But really, we can apply it to many more problems that have to do with string scattering. So let me mention a few. For example, we've looked at the cross sections, or total cross section for the string production. We've looked at partial waves. We've looked at the Reggie limits of these amplitudes, and we're really learning new things every day. So it's very exciting. So if you ask me after the talk, I could explain some of the more of the details of these constructions. But for now, let me just summarize. The summary is very, very simple. Okay, so first of all, I was trying to emphasize that it's not easy to use textbook expressions to actually compute scattering amplitudes. If by compute, you mean extracting numbers. Okay, there's a lot of subtleties. However, unitarity as well as causality give us a lot of guiding principles. And those guiding principles led us to a proposal for the genus 1 contours that I described here. And I actually described it in this talk for the planar contribution, but we already know how this works for the non-planar contribution, and as well as for the closed string scattering. This is scattering of gluons, at least for the imagery part. Okay, and then the final part of the summary is that all this built up to the first evaluation of the one-loop string amplitude at finite values of alpha prime. Okay, so with that, let me wrap it up and leave you with this plot.
Yeah, so John, and then.
Okay, thanks. Two quick questions. One is, I didn't quite follow when you talked about this semicircular contour and it being different from the vertical contour.
Yeah.
You said it wasn't a contour deformation, but it looks like one to me. I'm trying to understand what's, this thing is holomorphic in the upper half plane, so what's going on there?
Yeah, excellent. So you're completely right that the contour is, the integrand is holomorphic in the upper plane. However, it's not holomorphic in the neighborhood of the real axis. So the Cauchy theorem doesn't apply on the real axis.
Oh, because it's not even continuous to the real axis.
Yeah, there's an accumulation, there's a natural boundary of essential singularities.
And then the more substantial question was, in QFT, I can think of the I epsilon prescription as being something that you have to do because you were sort of making a mistake and treating a distribution as though it was a function, and you have to sort of regulate it to make it into a function that you're allowed to manipulate and integrate the way you expect. Is there a way of seeing some kind of story like that here, or no?
Yeah, the physical interpretation that you can assign to it is that in a sense, we're making an infinitesimal mistake when we treat the Riemann surface as a Euclidean surface. And the problem with that is that the target space is not Euclidean, it's Lorentzian. So in a sense, we're paying the price in the fact that we're not careful about these Lorentzian worldsheets. And you can view there's a sense in which you can view this analytic continuation here as, roughly speaking, in the neighborhood of these degenerations, you turn the worldsheets into Lorentzian worldsheets. So that's the physical picture.
Is the choice of the integration contour unique?
So as far as we know, this is the only one reasonable contour that we could come up with, and also that checked out with all the checks with unitarity cuts, for example. So it's the only one that we know.
There could have been different contours.
Yeah, so you could try to come up with a different one as long as it satisfies all the other constraints, then that would be another proposal. But this one is, of course, physically motivated.
Your contour prescription is very elegant, but I was wondering, in terms of getting actual numerical results, is it really simpler than just cutting off the singular point in moduli space and putting that contribution by hand as one would do in string field theory, for instance?
Yeah, that's a good question. I would say that we've tried a lot of things, and this is the thing that worked. The problem is really here that if you're trying to carve out some part in here, you're really hitting an infinite number of singularities. So the sign problem that I mentioned here is roughly in this neighborhood in which the function oscillates a lot, and that makes numerics essentially impossible. But this trick with mapping it to the circles is essentially what enabled us to do this computation in a kind of non-trivial way. So I think it would be excellent if there was some string field theory perspective on this that could help us with those computations, but currently we don't know.
I just have another question. I was wondering whether you have thought about this kind of loop computation in the light cone gauge, in the Mandelstam parameterization moduli space?
Yeah, this is, we've not considered it seriously, so I know that we've read some of the papers that did that in the past. And there, to be honest, even the genus 0 story looked complicated enough to me that I was not willing to do the genus 1. But maybe there's something there. We have not studied it exhaustively.
There's a question from Edward Witten online. Please.
You didn't say anything about the parameters that I think you called Z, the positions along the world, the edge of the world, boundary of the world line. So I assume that the I epsilon wasn't important for those parameters.
So yeah, excellent question. It's actually important there, but it's simple enough that it can be dealt with in the same way as the genus 0. And the genus 0 currently we have complete control over the I epsilon prescription.
I see. Okay. Thank you.
Thank you.
You mentioned at some point that the technical problem is the integrals high oscillatory, and sometimes with the complex integrals you can find the Lefschetz symbol where the phase is actually constant. Is it feasible in this case?
That's an excellent question. The most honest answer is that we don't know. So this is actually something that we're looking into now, trying to actually understand the saddle points, like which saddles are relevant to this contour specifically. And that turns out to be an incredibly complicated problem as far as I can see it, because of the bunching up of not only singularities, but also saddle points in the neighborhood of the real axis. And so numerically, we have some evidence that there's some families of Lefschetz symbols that should contribute to it, but we have not worked it out exactly.
Okay, no more questions also. So, well, let's thank speaker again.
Thank you.